Everyone. So in preparation for the final, several people asked me how can they get faster at coding, so that on the final that they can do better than they did on the midterm. And of course the way you get faster at coding is to code. And so I realized that there's a bit of a difference between the problems that we do on the homework and those that we do on the exam. In the homework, especially now that we're at the end of the semester, the problems are getting fairly involved. And the good part of what you get rewarded for in the homework is not just writing the code, but to come up with a way of solving it, come up with what sometimes is a really non-trivial solution. Whereas in the exams, there's just not that kind of time. The exams, even the final is it's over after a couple of hours. And so I can't expect that you come up with a solution for something really complicated. So the questions that are going to be in the final are, again, pretty much writing simple programs. So when you look at what was in the midterm, there was what was to compute the sum of a bunch of numbers or to compute the maximum of a bunch of numbers. I mean, those are all fairly simple and straightforward things. Or to draw a sequence of shapes that go this way or that way or both. And so I thought I'd just publish a set of practice problems, and I'll just do 2 a day. Totally optional. You don't have to do it. You can just ignore it. Or if you want to have some extra practice, then go ahead and do it. I'm going to do it in such a way that those of you who have a little bit of time, just do the first one, and I'll make the first one. I'll start with a bunch of easy ones, and then I'll ratchet it up a little bit. And then I have a second one that's a little bit more complex for those of you who have more time to devote to it. So you should expect to take, depending on where you're at, 10 minutes to an hour or so to solve one of these problems. And after you've done a few of them, you're going to see that you're going to get quite a bit faster at it. So I'll pick most of these from Coding Bad or from the from NetBrat. And so they'll be where you can just hack away inside that site. You don't have to do anything with BlueJ or anything. You don't turn them in, but if you have questions about them, feel free to discuss those questions on Piazza. All right. If anyone else has any remaining issues on the exam, send me a private email. No one else wants to hear your problems. Flash drives are here. Those of you who want to pick one up, pick it up after class, so we don't have a wild commotion right now. Yeah. Oh yeah. So here's the thing with I have no idea what those numbers mean. When I look at the spreadsheet that Canvas gives me, it has a column that says final score. I hope you get to see that one as well. And it's something that Canvas cooks up from all of the various scores that it has. Right now, the final scores that are being reported to me range from 0 to 52%. So if you find a number that says final score that goes from 0 to that's somewhere in that range, and you want to know how you're doing in class, then look up in this list. Let me find it. Yeah. So I posted the column of numbers after sorting it by that column that I got. So let's say that you have a final score of 37.4. So that would put you right here, and then you'd have to count how many numbers are above. That gives you your standing in class. And so whoever was with 37.4, I'd say it looks like right now the guesstimate would be a B minus. Just guessing. So that gives you a rough idea of where you're in class. And unfortunately, that seems to be the best that I can squeeze out of Canvas. And again, why it comes up with the numbers like this, it's beyond human comprehension. So if you can't find that final score, let me know. Unfortunately, I don't really know what it looks like from the student side. I made myself a student in another course, but I see different things there. So try, and if it's confusing, start another topic on Piazza, and I'll be glad to have another look at it. So I try to rig it so that you have some idea where you are. And so you can't simply say, well, I had 77%, so therefore I should be getting a C or whatever 77% might be in your psychology class. It's different. And ultimately, the reason why it's so difficult to do it is that in many classes, you're pretty much rewarded for memorizing stuff and doing fairly simple things. And here it's just not like that. I mean, you're expected to do things that are fairly complex, and it's just not the case that an A is 90% or above. You'll see later that the students who get an A, they were able to do maybe 70 or 80% of the work. That's normal. Other questions? That's normal. I mean, we'll know when the final curve comes out what an A actually was, but it might be like 70% of all total points. There's no way of knowing until I do the ranking what an A is in any particular subcategory, right? There's an A for the homeworks. There's an A for the exams, an A for the final, and each time it's really difficult to see what that is because I don't know how the curve is going to come out.
Okay, so if we go into capacity or see what our ranking is that still relevant information?
I think it's a reasonable approximation. I've been looking at a bunch of different, who comes out on top, who comes out on the very bottom, who comes out in the middle, and it seemed to me, just looking at, from my experience, where these people would likely be, that the computation that Canvas does seem to be a reasonable approximation. So I think you should go by it as an approximate idea of where you are. That's why I'm publishing them. So I just hope that you can look at those same scores. Why those scores fluctuate as crazily as they do, I simply do not know. I'll understand it eventually, but I just don't understand it today. But I've looked at like the top 20, and they were all names of people who looked like they were doing very well, and it seemed like they were going to be getting an A. And I looked at the ones at the bottom 20 and did the same. And I looked at a few in the middle. So I do think it's more or less okay. All right, on to the lecture. So we're going to be continuing that section on array algorithms, and then we go on to two-dimensional arrays, which are, if nothing else, important for the next homework assignment, for the one that comes after Thanksgiving. So my apologies for having messed up with the dates. My intent was to have the current homework assignment, have the draft due today, and have the final due on Wednesday, so that you have to work over Thanksgiving. And I forgot to shift it. So now the draft is due on Wednesday, and the final one is due on Sunday.
Tuesday, right?
It's due on Tuesday?
Well, Tuesday at 11:59.
Whatever. I'm not going to mess with it. Then it's due on Tuesday. Yes, yeah. On Tuesday, right. And so anyway, so my intent was to do different, but now you have to follow what it is. So, but if you want to keep your Thanksgiving free, the solution is, of course, simple. You're allowed to send it in early. All right. This algorithm here to find a value in an array. So let me just draw a quick picture to make this less abstract. So I'm supposed to find the first number that is bigger than 100. And it's pretty obvious on how one does this, right? You look up at index 0, you look up at index 1, you look up at index 2, and as soon as you find one that's bigger than 100, then you stop. And so the reason we're not using a for loop here, but a while loop, is that if you used a for loop, that would mean you would go through the entire array all the way through. It wouldn't capture that, and then you stop. So instead, we're using a while loop. And so the while loop has two criteria on when we keep on going. We could keep on going while we have valid indexes and while we haven't yet found our target. So it's possible, of course, that none of the elements in the array match the target. You know, the array might have just contained small numbers, and in that case, we need to stop before we fall off the cliff here. And it's also possible that we have found the value, so that's the second criterion. So that's why you have two termination conditions here. So, and here now we do two things. If we found the match, then we set that Boolean variable to true. That way, next time around, the loop is exited. And otherwise, we increment the position. So why not increment the position both times? Because this way, when we come out of the loop, then pause stays at the index of where we did find the match. So in the case where we found the match here at offset 2, pause would stay at 2, and we can later look up at position 2. That's where the match was. And of course, we can look up at values bracket 2, values bracket pause, and that gives us the value that's there. So that's the basic idea of finding something, and it's obviously pretty simple. Now, to let things going with the clicker question, that algorithm that I've just shown you locates the first match. What if you want to get all matches? And I'm giving you a few suggestions, and I'd like you to tell me which one or which ones of them you like. I'm sorry? Oh dear. All right, so option number 1 is you can collect all matching values in an array list of doubles. So remember, the total array of values contains doubles, so that's the way we could collect them. You could collect the positions of the matching values in an array of integers. Option 3 is you can supply a function find first that takes two parameters, an array of values, the limit. In this case, we want to find the ones that are at least the limit, and the starting position of the search. And presumably, it'll return the position of the first match and call it repeatedly. And option 4 is that all of the above will work. Okay, I would have to have someone show me what Canvas looks like from a student perspective. Maybe we can do that after class.
Okay, thanks.
Okay, while you work on that clicker question, let me see how one might do the first option. So in all of those situations, when we want to collect all matches, we would have to give up on the idea of traversing all elements. Instead, when we find a match, that's the case here, we want to spring into action. And what we might want to do is put the matching value in an array list, so that might be result. So add of, what was it, values dot get of I. Then over here we'd have to take out the else, of course, because we want to keep on going in all cases, not just when we found a match. So with this adjustment, it looks like this loop would in fact catch all matching values in an array list. Now let's say we want to do a slightly different thing. What if we want to catch all matching positions in an array? Then over here, so again, we would take out this thing, we would take out the else. Then over here, we now know that we want to collect pos in an array. So I have an array of values. I'll put it on here, int result. And so over here, I would want to say result bracket something equals pos. What index? So the challenge here is that if we look at the example over here, we would have a match here and we would have a match here. This one here would be the 0th, and this one would be the first one. So it looks like I would have to keep a separate excuse me, a separate index to keep those. So let me call it j. And after that, I would have to say j++. And that brings up the second issue. How big should I make this array? See, an array list grows and shrinks on demand. I can start out with an array list of length 0, but with an array, how big would I have to make it? How many matches could there be? I mean, obviously, I can't just say 2, because there might be more than 2. Yeah? I could start it out at 10 and then keep growing it on demand, but that actually turns out to be really painful. We'll see that in the next few slides. And so in this case, what I would do is I would set it up with the worst case. What's the worst case? That all of the elements match, right? So I would say it's a new int values.length. And that would actually also work. At the end, I would need to hang on to j to know what is the last index, and that would be a working solution. So at this point, it becomes clear that the answer must be what it is, because there's more than one correct solution. So let me turn the poll off. Oh, close. Okay. And so that's in fact the case. It refuses to close. There we go. And that was also the majority answer. So let's see what is part 3, option 3. Option 3 is to have a function that you would call repeatedly, and you know that works because that's the same idea as an index off for a string. The string index off searches for a matching character, and it gives you the matching index. You want to find the next one, you call index off again with one more than the previous match. So that'll also work. All right, now on to other algorithms. Removing an element. So let's say we have this array here, and for whatever reason, I want to remove the 103. I've never liked the 103. I want to be rid of it. And there are two ways of doing that. Number one is, if I don't care about the ordering of the values, then it's actually pretty easy to get rid of the 103. Namely, what I do is I pick the last element and put it in here. The 103 is gone. All the other elements are still there. They're not at the same position, but maybe I don't care. And so that's the first algorithm that you find here. That value size variable is a variable that keeps track of how many elements in the array are important. Obviously, if you remove something from an array, then you need to keep track of how many elements the array contains that are actually of interest to you. Oh, I skipped the first bullet. To remove something from an array list, you just call the remove method and you're done. This is only for arrays that you need to know. Well, now let's say you have an array and you want the 103 removed, but you want to keep the order of the other elements. Then what you need to do is you need to copy this entry over here and this entry over here. and you still need to reduce the size of the elements. That way, the 20 wipes out the 103, the 104 wipes out the 20. You actually still have another 104, but you need to then make sure that you've reduced the size to now only count until here. So that's the second algorithm here. There's a loop here that copies the values over. And you see I'm copying from I plus 1 to I, and you see that over here. I'm copying from the higher index to the lower index. All right, here you have the same picture again. Now for insertion, it's the exact opposite. So let's say that I want to insert the number 42 at this point. So, yeah, I guess if I didn't care where I want to insert it, I just insert it at the end here, and that's the easy case. I'm not really going to talk about that anymore. But let's say I want to put it at a particular point and preserve the ordering. So then I need to do what? I need to move these ones here out of the way, copy the 104 over here, copy this one over, copy this one over, and then I can write my 42 into here. And that's the code that you find here. So I'm looping. This time here I'm copying from smaller indexes to bigger indexes, from I minus 1 to I. That's the direction that you've seen here. When I'm all done with the loop, then I'm putting the new element at the slot that has now become free, and I increment the total size. So there's a bit of a subtlety in this loop, and that I want to explore in the next clicker question. Let me set it up, and then I'll explain it to those of you who can't get at it. Oops, hang on, need to add an option. Okay, all right, so here I've changed the algorithm a little bit. If you look carefully over here, you'll see that the index values went from the top to the bottom. And it seems kind of complicated. So over here, I've done it a little bit simpler. I go from the position until I go to the top in the usual way. And I want you to find out whether it works. So run through this algorithm in your mind, or even better, on a sheet of paper. Start out with this particular array. We want pos to be 3. We want to insert the element 10. And then tell me what comes out after you've run through this algorithm. Oh, sorry. Okay,
Your site's not available, so we can't refresh on our own computers.
Uh-huh. Yeah, I'll move this. So let's see. So pos plus 1 is 4. So I is 4. So values 4 becomes values 3. 2, 3, 0, 1, 2, 3, 4. So this one here becomes 16. Then I becomes 5. So now values 5 becomes values 4. This is actually bad. What's happening? Yeah, so it looks like that 16 is going to get percolated all the way through, right? Because the next, it's going to happen again. Value 6 is going to be value 5. And so the 16 fills up everything. Why? No, it's because we're going in the wrong direction. So let me first of all close the poll whose answer should by now have become obvious. Yeah, I know it's a good poll here. Close it. Okay, and do we get a majority answer for this one? Yes. So the problem is that when you work in that direction, when you copy this one over here, then you wipe out this one here, and then you copy over here, that's no good. That way you have the same entry just filling up everything. Instead, what you need to do is you need to go the other direction. You need to copy starting from these indexes and move your way down. So that way the 36 comes here, and then we move our way down, and the 25 goes over here. And then we move our way down to yet another smaller index, and then the 16 finally gets copied over here. So that's the remarkable thing about insertion versus removal. You just have to know that you have to set them up in two different directions. Myself, I can never remember which direction is which way, and so I always just make this little sketch to see which way it needs to go. But what you do need to remember is that there is this potential pitfall that they go in opposite directions. All right, now copying an array, this doesn't happen anywhere near as often as you would think, but once in a while it does happen. The reason you want to copy an array is that, as you know, that an array, as it's implemented in Java, when you have an array variable, you just get a reference to the actual array, and if you have two of those references, and you mutate through one of them, then the other one sees that too. Sometimes that's what you want, sometimes it's not. If it's not what you want, you have to make an actual copy where you would get a new array hooked up to the second variable like you see in this picture here. And it's easy enough to do. There's a method that does that called arrays.copyof. And I don't do it often enough that I would actually remember the name of the method, but I remember where to find it. It is in whatever that section is, somewhere in chapter 7, and there I can look it up. So it makes a true copy of all of the elements in an array. It's simple enough. Now, the one time that it's kind of useful to know about this is if you're in the situation that one of you just brought up with this idea, can I start an array that has size 10 and then make it bigger and bigger if I need new elements? And that is really a situation that does happen occasionally in practice, that you're forced to use an array for whatever reason, and the array, you don't know how big that array should be, so you start out with size 10, and then as you need more space, then you make yourself new space. And so the way to do that is as follows, that you call the copyof method in this particular way. You say, I want to have a copy of the array values. I want it to be twice as long as it was before. And I want to capture it again in the same variable. Yes?
I know that with the copy of, it says that like if it's a little bit longer than what you want to copy of, like if you set the length a little bit longer than what
Yeah.
you want, it says it fills it in with false. How does it do this?
Well, it fills it in with false, zero, or null, depending on the element type. So over here in this example, that white area that you see down here, that's not all going to be filled with 0 because it's an array of doubles. If it was an array of Boolean, it would be false. It has to fill it with something.
So, but how do you get it to double perfectly like that? Like if you
Oh, you just tell it, I want it exactly twice as long.
And then it would automatically just fill it in twice. It wouldn't put.
If you make a call just like it's here, it'll copy as much as it can, and that's the original length. And when it runs out of stuff to copy, I mean, the original one was this long, and
So if it can fit both of, if it can fit it in twice, then it'll be twice, but if it only has room for 1.5.
yeah, if you for whatever reason were to say here 3 times over 2, because you don't want to grow quite as aggressively, then the way it would look is that the first 10 would be copied over, and you would get 5 zeros after it.
So it wouldn't copy just part of the rest.
It doesn't copy the rest. It copies what it can, and it fills the rest with the default. All right. So this is something that does happen occasionally. You will see it in 46B when you learn how the array lists are actually implemented. They're implemented in just this way. We've seen printing element separators, and I don't want to talk about it. Or do I? No, I don't want to talk about it. So I'll ignore this clicker question. I want to talk a little bit more about two-dimensional arrays because the book's not really very verbose about it, and it's important for a couple of assignments. So a one-dimensional array is, at this point, should be kind of obvious to everyone that you have a linear sequence of numbers. Doesn't have to be numbers, but often they are, like that. Now, what if you have a two-dimensional arrangement? With rows and columns. And that often happens. That grading spreadsheet that I've been staring at over the weekend looks like that. You have rows and columns of numbers. And in that kind of, there's no special Java class for that. In Java, instead, these are implemented as arrays of arrays. So the way that Java looks at such a thing is that each row is a separate array, and then you have another array that points to each of those guys. And so that's why there's not much syntax that you have to learn. The only syntax that you do have to learn is how to allocate one of them. So here I've done it not with numbers, but with strings for tic-tac-toe game. So obviously a tic-tac-toe board is a 3x3 arrangement. And so the way you make one is you use 2 brackets instead of 1. So here you have bracket 3, or because I want to leave the rows and columns potentially changeable, bracket rows, bracket columns. That makes an array, this two-dimensional arrangement, and it fills each of the cells with what? With null. Very good, right? Because it's an object of a class. It's not a number, it's not a Boolean. So now I have 9 nulls neatly arranged. Of course, I don't want nulls. I want to change them in some way. Oh, notice also the type of the thing. It's perfectly logical. It's now a two-dimensional array with 2 brackets there. And yes, there are 3-dimensional arrays, but we're not going to cover them. They're very rare. Like if you wanted to model Rubik's Cube, you could profit from a 3-dimensional array, but we're not doing it. So now we have an array of 3x3 or 9 nulls. And we want to quickly get rid of the nulls, so we want to fill them with something. So over here, I filled one of them. That's the element at row 1 and column 1 with an X. That's what you see here. And then at row 2 and column 1, I filled that with the letter O, and that gives me that arrangement. So notice that the way that the syntax is, you just use 2 brackets where previously used 1. The first one is for the row, and the second one is for the column. Now I said that technically in Java, a two-dimensional array is an array of arrays, and so if you think about it, the row index would pick you the row, and then inside that, the column index would pick you the column of that row, and that's how the 2 brackets are implemented. You don't really need to think about that every day, but it's it's interesting to know that that's how it works. So, so you have this two-dimensional array, and you can access any of the elements in this way. Now, how do you traverse it? So let's say that we want to fill the entire two-dimensional array with spaces. you know how to fill a one-dimensional array with something. You would say for I is 0, I is less than values dot length I plus plus values bracket I equals 0. So you have a single loop to fill a one-dimensional array. Yes?
Would it just be precise? Would it be values at length minus 1? Or would it
I less than.
Oh, okay, okay.
Yes. So it's an asymmetric bound, and generally you prefer to use these asymmetric bounds with anything that has a length, like an array or a string or an array list. So over here, for a two-dimensional array, we're making two loops. One that loops over the rows, and then inside that, one that loops over the column of the row that we're currently looking at. And so here we have two indexes, row and column. And then we use them both in here, and we say we want that thing to be a space. Now, this is probably all that you need to know for 46A in terms of how to do this double loop. Notice that over here I don't have to remember the number of elements in my array. I can just call values.length. But over here, I've remembered the constant row and the constant columns. Sometimes that's a little inelegant to have to schlep them around. You can recover them, but it's not totally intuitive how. So, and for that, it does really help to know how arrays work internally. So board was the array. Board.length is, when you look over here, it is the length of this array, because that is actually what board is. It's an array of rows. And so that's the number of rows. How about the number of columns? Board bracket 0, this is this guy here, which itself is an array. That's why it's an array of arrays. And the length of board bracket 0, that is the number of columns. And so if you don't want to carry around the rows and columns as constants or variables, you can recover them like this. Now at this point, everyone should ask, what about board bracket 1.length? Well, if you made the array so that all of the rows have the same length, then of course that's the same as board 0 length. And that is the way that it's made by this constructor. When you call a constructor like that with the two brackets, it always makes a rectangular array where all the rows have the same length. It is possible to make ragged arrays where all of the rows have different lengths, but we're not going to cover it. So in the context of this course, it is perfectly acceptable to just do board 0 length. If you really wanted to be finicky about it, you would say, board I.length, and that way you could even deal with a ragged array. But you don't have to do that in this course. So that's all that they tell you in the book about two-dimensional arrays. And then it's a little unfair that now come 20 assignments that you couldn't possibly solve with just that knowledge. But so to demystify that a little bit, I thought I'll just talk about one of the upcoming homework assignments. So one of the upcoming homework assignments, you have the following challenge. You have a two-dimensional array. You have a particular location of it that's given by a row and a column. And now it asks to count the non-zero neighbors. So it asks how many of the neighbors are not 0. And so what's the big deal? You know, how many neighbors are there? 1, 2, 3, 4, 5, 6, 7, 8 neighbors. And so, sorry?
I don't know, I thought you were just asking for musings on how to solve it.
Yeah, muse away.
So you have to find some kind of pattern that would go through all of those numbers.
All right, let's try that. So let's just pick some sample value, and let's say the row is 6 and the column is 10. And let me switch colors here. So that means that this, again, this one here is column 10, row 6. What's this one? That is row, you do the row first. Row is 5, 10. What is this one? What is this one? 5, 9. I'll put it up here. Okay, what's this one?
6, 9.
Okay, this one is 6, 10, which we're not counting. Okay, and then this one is 6, 11. And this one here? Yeah, then we have 7, 9, 7, 10, and 7, 11. So what you can see is the rows go from 5 to 7, or in general from 1 less to 1 more. The columns go from 1 less to 1 more. But you have to skip the one in the middle. So if I were to code that up, which lecture are we at? 21? Let's call it a board. So then I have a counter, of course. I now have these 2 loops where the row goes from, no, I can't use R. I goes from R minus 1 and the column goes from column minus 1 yeah, thanks. So if values ij not equal 0, counter plus plus. When I'm all done, I return my counter. We put some test data in here. There's another way that the slides didn't show, but the book does show, to initialize a 2-dimensional array. Use these braces inside braces. Thank you. Yes, I do. I just want to put some boring values in here. We can fix those later. So notice the braces inside the braces to do the initialization. It's like I said before, it's an array of arrays, so you really do stick a bunch of arrays in here. And here you could also make an array that's ragged if you made these different lengths. We're not going to do that, but one could. All right, so now you said very correctly, so I have to worry that I don't check the middle one. If you look at over here, that's the one that I had boxed in here. I have to skip that one. Okay, that's the one where, so the middle one, I equals row, and J equals the column. So I don't want that to be the case. So what didn't I want to be the case? I didn't want I to equal R and J equal the column. Note I need to put the parentheses around it. All right, so let's try that. And we're going to look at, I'm sorry? Well, let's look at one example, right? Let's look at the case here where row is 2, column is 2. And in this case, we would expect the answer to be 5 because we have 1, 2, 3, 4, 5 non-zeros. So that'll be my test case here. So row 2, column 2, and okay, out of bounds exception. Why am I out of bounds? Yes? Excellent, yes. So I made the first error out of the book. Every one of you is going to make this error at least once in your life because your fingers are at this point so much on autopilot to type I++. I swear, I do this one every few months. So, and it really is kind of, it's not my fault that I'm making that error. It is totally the fault of the designers of this for language, because in other languages, the for construct doesn't have 3 different disconnected pieces that could be anything at all. The idea of the for loop is to loop through these numbers. And I shouldn't have to say I 3 times. 3 times I shouldn't have to say it. Not 3 times I should have to say it. Right? I should only have to say it once. And that's the way it is, though. But it's a very common error. So let's fix that real quick. And now I get the answer that I expected. There are 5 non-zeros around that. Well, that was good, so let me do it again. So what about the top left corner? I thought I just fixed that. There is no position -1, right? And so this is something that in this particular problem is always annoying, that the situation is different if you're in a corner or on the boundary somewhere. And it's just life, right? Because at that point, you can't go into the middle. So you really, at this point, also have to say they shouldn't be the same, and I should be at least 0, and I should be less than, what is the number? That would be values dot length. That's the number of rows. And j should be greater or equal 0. And j should be less than values 0 dot length. That's the number of columns. And there's an and here. Let me move this and over here for beauty. They're all in the same spot. So that's quite a condition. Let's just try it, and then we'll look at it one more time. Okay, it says there were 3 non-zero neighbors. Let's have a look at the code. And that's actually true, because we were over here, and my 3 neighbors are this one, and this one. So it does compute the right answer. What's that? So let's, now that it does seem to work, let's have one more look at the code. So we increment the counter if 6 conditions are fulfilled. We're not looking at ourselves. That I is a valid index because it has to be not negative, and it can't go above the number of rows. J can't be negative, and J also can't be above the number of columns. And finally, the condition that we're really caring about, that there is a non-zero entry. Yeah?
On the third row, or 2 rows under if, you've got a second statement of and,
Oh, that's a mistake.
but that,
That-
the program still runs.
No, I'm sure it wouldn't have compiled. I must have hit undo or something.
So is this, I mean, it works, is that many if conditions, like, does that seem excessive? Should there be affiliate with it? Or is that good?
Okay, that's a great question. So if you write that many conditions, would you now start saying, gosh, that does seem kind of crazy? And particularly, if I only write it once, I might just make a comment over here that says, I and j are valid. And in that case, when I come back to this thing and before saying, oh my God, I say, oh, that's actually not so bad. Because once you know what you're trying to test, it's pretty clear that it tests that. But now suppose that you run into this thing 2 more times as you solve your problem. You could, of course, copy and paste the code, but then it really does become kind of hard to read. And so what a lot of people recommend at this point is to say, when you have something that's kind of nasty like that, turn it into a separate method. So here goes. So I'm just taking it out. Now I don't want the comment. And then over here, I would say, if they're not the same, and is valid ij. So now I only have 3 tests. I say if they're not the same, and if ij is valid, and if it's non-zero. And that's pretty nice. Yeah.
In general, when you're coding, the less amount of code you type, the better the program will run, or the better the programmer in general.
No, I mean, there's 2 different questions. There's a question of execution time,
Right.
and there's a question of maintainability. And execution time, it doesn't make much of a difference one way or another. So in the 2 scenarios that you've just seen, it's essentially going to make no difference. Any compiler will be able to look at this thing and see whether it's worth inlining the function, meaning calling it in place, or whether to actually make a function call. So don't worry about execution time. The only time in general that we worry about execution time is if you loop over like millions of elements. At that point, there are better ways and worse ways of doing it. For these simple things where there's just one decision that could be done one way or another, the execution time never will matter. Just a second, I'll come to you. The second question is, what about maintainability? Because the biggest cost in developing software is the human cost, the cost of the programmers who need to fix it up, fix the bugs, and to deal with it. And in terms of maintainability, this version wins hands down, right? Because you can read this after half a year, and you can say, oh yeah, is valid. Now you have an intelligent name. The other good thing about it is, what if that same decision needs to be done elsewhere? You now have a canned method already that does it for you later. So from a point of view of maintainability, this is a huge, huge win. In fact, now one could say, maybe one should even go and do something about this, and I'll come to that in just a minute on how one can improve that. You had a question over there.
Just really quickly, this seems like an effective method, but sometimes in the homework you ask for us to write certain methods.
Yes?
If we wanted to split a necessary method into 2.
You can totally do that. So, and I highly recommend that. And there were a few solutions, when you look at my solutions, where you saw me doing that, where I came up with some methods that I hadn't specified that simply broke the problem down. And so I highly encourage you to do that. If there's any way that you can do to structure your homework more elegantly, the testers will pass. The testers will not call your handcrafted methods. And so now you know enough about programming that you can make these decisions. So, now I'm on a roll here, and I would kind of like to say, gosh, I have to compare these two things here. And I could, of course, now write a method that says, where I say these are the same location, and then here I would say, if not, is same location, I, J, or C. And over here, no, when at the same location, and that'll work. But, well, look at that. I mean, that's not the prettiest thing ever, right? So at this point here, it becomes apparent that we're always going to be dealing with pairs of rows and columns. And when you do more sophisticated computations in these two-dimensional arrays, which you do all the time when you model like maze escapes or games or anything like that, there actually is a big win to realizing that these row-column positions are kind of unavoidable. And you want to look at the row and the column together as a position object or a location object. And let me double check how I called it in the homework so I don't introduce two terminologies. Yeah, I never had trouble getting on my site. It's just you guys. I don't know. Location. All right. So let me introduce the same class here. And then we can compare two locations by saying return row equals other.row so that's when two locations are equal. And then over here in the other code, where is it? We would now want to phrase things in terms of location. We would over here, we would just pass in a location. And over here, we would say, if not, Al equals. And actually, that's a terrible name. Let me call it neighbor. And then over here, I would have to still deal with is valid, so I would put this one also in there. Over here, of course, now I would have to get the I and J out of it, so I would have to say neighbor row and then the column. And then I would get going. So when one does that, that it turns out there's a great advantage to having that. And in this homework, in part B, I will make you use those classes. So I'll give you the location class, and I expect you to use it in this way. Now, to motivate this thing just a little bit, when we look at this homework assignment, so it asks you to count the non-zero neighbors. I've pretty much shown you now how to do this. It asks you also to give you a list of all of the non-zero locations in a grid. So if we looked at this particular grid here, then we would want to get the location (0, 0), the location 0, 1, and so on. You would get a list of, I believe, 16 locations out of here. And finally, it asks you, given such a list of locations, that one should be able to set them to a particular value. And now you might say, why on earth does one want to have all of these methods? And the reason is that it gives a way to program a well-known game that I'm going to show you really quickly. And hopefully that'll at least mildly increase the enthusiasm for this assignment. And here it is. And now if I could just figure out how to scroll. Hang on. No, that was not the best fit. Here we go. All right. So, so many years, probably before, no, computers existed, but they barely existed at the time. This fellow came up with a simulated life where the rules are as follows, and you may have seen this before, where you have some random population of life on a grid where a blob means a cell is living there and empty means there's none living there. Only one cell can populate any particular location. And then the life unfolds over multiple generations. In the next generation, there's a couple of rules. If you have an empty cell that's surrounded by exactly 3, a new cell gets born there. I don't know why 3, but that's how it is in this particular one. And if you have a cell that's currently alive that has either only one neighbor, then it dies, one or no neighbors, then it dies out of loneliness, or if it has 4 or more neighbors, it dies out of overcrowding. So those are the only rules, and those are the rules that I'm trying to capture with here. I want to know for a particular one, how many neighbors does it have? And I want to be able to to loop over those and collect them. So here I want to find out, give me all of the ones that have 1 neighbor, 2 neighbors, 3 neighbors, and so on. And then I'm going to do something with those locations, namely fill them either with 1 or fill them with 0 to establish the next generation. So now what's kind of fascinating about this arrangement is that these rules are totally simple. And when you try it out, and I'll give you a program that actually implements the rules. You don't have to do that. And you can put in some populations, and you let it run. You'll see that kind of a random population, a lot of them kind of die out because they get lonely, and you would expect eventually they might be dead. They can't get too overcrowded, because if they start mushrooming, then the next generation, so many of them have too many neighbors that they die out of overcrowding. So you would expect mostly that there would be a colony collapse. And that has turned out not to be true. That the game has been cleverly designed, that there are these periodic things. If you come up with a thing that looks like this thing here, after 4 generations, it repeats itself, but one position down and to the right. And if you put one in, you will see it moving across your screen. So that'll be the reward for having implemented your methods correctly, that you'll be seeing it like that. Then you can take 2 of them and let them run against each other and explode in a collision and see what happens like that. So be like a nuclear physicist of the game of life. And so all of that was kind of nice. And this fellow Conway published this in, I think, in Scientific American. And then some 12-year-old kid who had nothing better to do in his life, remember that was before computers, send Conway a letter and say, look at this thing here that has the blob over here and these blobs like this. And now run it. And after, I believe, after 30 generations, so you run it for 30 steps, and this thing turns, in the meantime, it changes in all sorts of other shapes. But after 30 steps, it looks exactly like it looked before, except it has emitted 1 glider. After 60 steps, of course, it looks exactly like it did before, and it has emitted 2 gliders. So this thing is a thing that produces an infinite stream of gliders. And it's kind of amazing what you see it, but what to me is amazing, how did that 12-year-old kid do this? And I have no idea. I guess he had more patience than you and I will ever have. So you'll be able to see that out of this application. So what do you need to know in order to do this part B, which is a little intricate? You need to do that counting thing that I talked about, where you need to be able to loop over the neighbors and deal with the error conditions. You need to, non-zero locations is really nothing. You need to go through the entire array, rows by columns. There's code for that in the book. And if you find a location that's non-zero, just return it.
Find a location that's non-zero, then what?
Yeah, you want to. I want to collect them all, the ones that are non-zero.
Okay, turn it into the array.
Yes. And then here I want to collect the locations that have, this many non-zero neighbors, 8, 6, 3, or whatever. So you can think of the first one here is the union of all of the others. And finally, the setting one is also simple. You need to loop through this array and call the setting. You'll be able to do that one. The one that I think everyone finds challenging at first is this one, and I've pretty much shown you how to do that. All right, the third assignment here that, the pictures didn't show. Well, I'll have to make the pictures show and show it to you on Wednesday. All right, any questions before I call it a day? Yes? 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 Hang on. What the? Okay, it was string 2. Which? Yes? There's a Y here and there's a Y here. There's an A. If there are if there are characters both before and after. Remember to take a USB stick, so I don't want to take one with me. If there's not on both sides, it doesn't matter. So you have to check whether the position is in the middle, and then you check both the left and the right.